Okay, so here we go. This is 5.3. It's the fundamental theorem of calculus. So you would think this is kind of important, right? Which it is. One of the things that we need to realize is in the fundamental theorem of calculus, there's two parts. The first part is talking about making a connection between the derivative and the integral. And the second part is talking about the bounds, the upper and lower bounds, and how to use them. So it's kind of funny to me. I think it's actually better to teach the fundamental theorem of calculus part 2 before part 1. But I won't do that today. I'll just show you the way it is, and then we'll go from there. And you can ask questions if you have any questions on what I'm doing. All right. So what the fundamental theorem of calculus part 1 says that if we have a continuous function on a closed interval from a to b, then the function g, which is a function that's defined by an integral, by those bounds, is going to be continuous and differentiable if the derivative of g is equal to the function of f. So the important thing is here, so g of x is an integral that's going to go from some bound. Notice that it's going from the lower bound, but it's not going to the upper bound. It's going to a variable. And so what's going to happen there is that variable, when we do the integral, is going to become f of x. Okay? So let me show you an example, and then we'll be able to better understand what's going on here. So the crux of the problem is it talks about the derivative of g being equal to f of x. So if we're going to go find f of x, we need to take the derivative of this thing. Does that make sense to you all?
Yes.
Okay. So my g of x is this, right? Taking the derivative of g of x will yield my f of x. So what ends up happening here, though, is it's something interesting. So in this example, I don't want to get all complicated and show you the integral of secant x. So at the I will show you one that's very doable as an example for you to understand. But this first one, you're just gonna have to trust me, okay? So I'm gonna show you the basics of it, and then I'll show you some examples where we're doing the integral and going from there. So here's what's happening. This piece here is going to be differentiated. So what is the derivative of x to the 4th?
4x cubed.
So we're going to get 4x cubed. So that's the derivative of it. And then all we're going to do with the inside piece, the function, the integral and the derivative cancel each other out, correct? Because they're inverses of each other. And since they're inverses of each other, all I'm going to get is secant, but the difference is it's going to become x to the 4th. It's going to be the actual value that's plugged in. Notice the lower bound disappears. And the reason that the lower bound disappears is because if we would do the integral, right, we would have gotten... what is the derivative of the bottom? That lower bound?
Is 0.
It's 0. So 0 times secant of 1 is going to be 0. So that's going to drop out. So we don't need to worry about that if it's a constant. If it's a variable, then we need to be concerned with the variable. Now, let's do an integral that you should be able to do. Okay? So I can demonstrate it to you guys so that you better understand. All right, so let's say that I wanted to find the integral from, who cares, 7 to x of 6t squared dt. So if we want to do the integral of this, what's the integral of t squared?
The derivative of x?
No, the integral of t squared.
2x? I'm not sure.
No, that's the derivative. That's the derivative. So how many of you guys have actually watched the 5-2 lecture? Yeah, that's what I thought. If you don't watch the 5-2 lecture, going forward, you're going to be in trouble. So I strongly recommend that you guys watch that. I'll show you. So just so you have it. So the integral of x to the n dx is a power rule that tells us that I go x to the n plus 1 over n plus 1. And if it's indeterminate, I'm going to add a constant, right? But this one's not indeterminate, so it's just going to be this. So in this example, if I have the integral of t squared dt, that's going to become t to the square plus 1 over 2 plus 1, which is going to give me t cubed over 3. That's, you got to do it. You can't put off your homework, guys. It will be devastating. These next 2 chapters, if you don't have your integrals down, it will harm you. So I strongly recommend you put in quite a bit of time doing this work. Because the connections to what I'm trying to demonstrate to you right now is something that you need to be able to understand. So when I do the integral to this, I'll just move on. It's going to be 6t cubed over 3 evaluated from 7 to x, but then I still need to take the derivative of that. So when I evaluate this, I'm going to get the derivative of 2x cubed minus 2 times, and I'm just going to do 7 cubed, who cares, right? But that's just going to be a constant, correct?
Yes.
So when I take the derivative now, I'm going to get 6x, right?
Yes.
Squared minus 0, which is going to give me 6x squared. That's the long way. Not all of these will you be able to have the techniques to integrate. So the easier way to do it is, what is the derivative of this?
0 or 1.
It's 1 times 6, but now I'm substituting t, I'm going to make it an x squared, and that becomes 6x squared. So by understanding the process, we can save ourselves a lot of time. Does that make sense?
Yes.
Yes.
Okay. So the derivative of the variable in the bounds, and then that bound plugged into the function. So let me give you guys one to try and see if you can do it. Try that one real fast. You guys got it?
Almost.
It should be this fast. what's the derivative of that? 2x. Plug it into there. Boom.
Oh, okay. Makes sense.
Now, we could do the integral and then do the derivative, but we see that that's going to be a lot of work. So this is the shortcut to do it. Okay? Because I might give you integrals that you just cannot do. So if there's an integral you cannot do, you don't have the tools to do it yet, you can still do it. You can still do the fundamental theorem of calculus part 1 if you understand the process of doing it. Does that make sense?
Yes.
And what this ends up showing, is that the function f of x is continuous and differentiable. So there's fundamental theorem of calculus part 1. Big deal. I remember when I was in college, my professor actually asked a question about the fundamental theorem of calculus parts 1 and 2, and we had to prove it. So it was a little bit higher level class than this. And I went into the final, and I remember it's Dr. Watson, actually, the book that you guys use was written by my professor. And we were in class, and I think he liked me. And he goes, well, these are the things that you need to know for the exam, and blah, blah, blah. And I go, the fundamental theorem of calculus proof we need to know? And he goes, absolutely. And so he goes, hold on a second before we start this test. And he did the proof on the board for us all, right? And I'm looking at it, I'm like, okay, I got to memorize this thing right now because this is going to be on the test. And then he proceeded to erase the board, but he erased the board in such a way that we could see the proof.
Nice.
And everyone looked at me and were like, thank you. But that was our professor's grace more than anything else. But because of that, I've always known that proof. Because I was like, nope, I need to honor that guy for what he did for me. So this is a big deal. It's fundamental to this class, but understand this process. It will be beneficial and save you guys time. Okay, let's go on to the fundamental theorem of calculus part 2, and then we'll do a few examples so you guys can understand them. So the fundamental theorem of calculus part 2 is just telling us this. It's telling us that our function, right, the lowercase f of x is the function. When we have the uppercase, right, where it's a capital, that's the antiderivative. Okay? So that's notation. This is your function. This is the antiderivative. That's the capital F. Okay? And then what we're evaluating is at the upper and lower bound. So it's the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. So that's why we get f of b minus f of a. Does that make sense? And since capital F is the antiderivative, the derivative of capital F should then give us our original function. Does that make sense? Because they are inverses of each other, correct?
Yes.
Okay, so now here's where the practices come into play. What is the integral of 1 over x? Or better stated, what is the antiderivative of 1 over x? Please, not everyone at once.
Is it just 1 over 6?
No. Don't. This is not the fundamental theorem of calculus part 1. This is, and you would have gotten that wrong anyways, because what's the derivative of 6?
Oh, 0.
What is the antiderivative of 1 over x? Did you guys watch 4.9? The video for 4.9?
It was optimization, right?
No, I think 4.7 was optimization. 4.9 was the antiderivative. So, okay. So, there's some work that you guys need to do. But here we go. What function has a derivative that gives us 1 over x?
Natural log.
So it's the natural log, correct?
Yes.
So the derivative of the natural log is 1 over x. So we're going to get the natural log of x evaluated from 2 to 6. That's what you end up seeing in notation. That straight line right there means such that. Okay? So when we evaluate this, what we're going to end up getting is ln of the upper bound minus ln of the lower bound. But then, with logs, what do we know about minus?
Oh, then they go over like on one.
So it becomes a division, right? 6 over 2, which will then give us ln of 3. And ln of 3 is the answer to this problem. But it's imperative that we know the antiderivatives here. So if I had given you a general equation of 1 over x dx, then this would have been ln of x, and now we need to add the c, and the reason we need to add the c is because we don't have upper or lower bounds. Right? This is the indefinite version. If we have upper and lower bounds, then we do the fundamental theorem of calculus part 2. So this one will be FTC2 because we have the upper and lower bound. This one is just a generic indefinite. Does that make sense? So are there any questions so far?
I don't think so.
Okay, some things that you need to spend some time in. These two are big. Those videos are up. You need to watch those.
Yeah, I checked Canvas right now and I couldn't actually find the 4.9. I saw a 4.7, but I skipped. Like if you go to like lecture videos, is there anywhere is that on your YouTube?
Yeah, it should be. I'll make sure that it's up on the page for you guys. It's something that you guys should really look at. So I'll make sure it's up there for you. Yeah, 4.9, the antiderivative is just basically thinking of the derivative backwards. So something like this. So let's say I had, if I gave you this. If that's the derivative, what was the original function?
X cubed.
Almost.
Or x squared. Sorry, wait.
You're saying x cubed. That doesn't work, right? Because x cubed would give us what?
3x squared.
3x squared. So going backwards, what's going to give me 3x squared?
X cubed gives you 3x squared. But
Well, let's just look at it this way. If this derivative, if I take the integral of this, what's the integral of this going to be? So here's where going backwards is so important, and we'll spend some more time on this. It's going to become x squared over 2, right? So that means that had to be a 6. Ooh, I'm sorry, that had to be a 3. So 3 halves x squared, when I take the derivative, makes the 2 go away to go back to 3x. Does that make sense?
Yes.
Oh, I'm not worried about the plus c. I'm just trying to see, all right, what would get me there? You're right, you would have a plus c if you wanted in terms of the general case. But this piece right here is what matters. This will get me here. But if I give you this, can you get back to here, thinking backwards in terms of derivatives? That's the critical piece of what I'm talking about. Right? Because then eventually, I'm going to do stuff like this to you. 2 cosine of x. What is that? What would get me that? If that's the derivative, what was the original function? That's right, 2 sine of x. But we have to be able to think backwards and forwards, right? So if I had like, this is all stuff that if you don't know your derivatives, you're gonna get stuck with these problems, and I don't want that to happen to you. So understanding your derivatives and then understanding to be able to work backwards is so important, because that's what the integral is. It's really going backwards, right? To what you've learned thus far. All right, so look at this one. We're going to jump. So from here, what's the antiderivative of x, the cube root of x? It's probably too hard to see it that way, so it'd probably be easier for all of you if you saw it like this. Right? And from 5-2, I gave you the power rule, so you should know what the power rule is, right? I actually demonstrated it earlier too. So what's the power rule?
X to the n plus 1 over n plus 1.
That's right. So if that's the case, then the antiderivative of this would be 1/3 plus 1 over 1/3 plus 1 evaluated from 1 to 8. Right?
Mm-hmm.
And we can see that if we took the derivative of that, that would in fact give us x to the 1/3 power. Because look what happens. I get 4/3, right? And then it's going to be, let me erase that. That would be 3, that'd be 3/4, right? But when I take the derivative of that, don't I get 3/4 times 4/3 x to the 1/3? Which is x to the 1/3 exactly. So here's the thing with this stuff. You should always know exactly what you're doing and where you're at, because you can always check your work. I've always kind of marveled at people who leave a math exam and don't know what they got on the exam. I would leave exams when I was at college, and people would be like, "Oh, how do you think you did?" I'm like, "Well, I got number 2 wrong and number 8 wrong." And they're like, "How do you know?" I'm like, "Because when I tried to check it, I couldn't get the answer." And they'd be like, "Oh, I don't know how I did." I'm like, "What do you mean? Check your work." Don't you want to be absolutely like certain that you're right? I mean, I've always wanted to be that way. So this would be 3/4 x to the 4/3 evaluated from 1 to 8, which tells me I'm going to get 3/4, and I'm going to factor out the 3/4. So I'm going to get 8 to the 4/3 minus 1 to the 4/3, right? From the fundamental theorem of calculus part 2. That's going to give me 3/4. 2/3, that's going to go away. So 2 to the 4th is 16. Minus 1 is going to give me 3/4 times 15. Which is, what the heck is that? Is that right?
How do you get the 16?
Okay. 2 to the 3rd is 8, correct?
Mm-hmm.
4/3, what happens to the powers?
Oh.
They multiply, correct?
Yeah.
So I get 2 to the 4th, which is 16. I use power rule because I use the power exponent rules. I know that 8 is 2 to the 3rd, so I think as soon as I see a cubic in the denominator, I think of the base number and see if I can turn it into a cubic so I can cancel out thirds. Make sense? Yeah. Okay. What's that going to be? 45 over 4, which is 11 1/4. And then it's the area under the curve, so we should have some units that are squared. You guys are really quiet today. Are you tracking with me, or are you guys a little bit behind?
A little behind. Gotta watch the anti-derivatives.
Yeah, I watched 49. I just have to rewatch it again because I was a little stuck.
Oh, on 4-9?
Yeah.
Yeah.
I watched it once and then I'm trying to go back and like do the problems by myself, but.
Well, I can answer some questions for you guys on them today too, so that you guys can actually see my thinking, which could be beneficial. But it's the backwards thinking that matters, right?
Yeah.
So and I know that's kind of weird because you've gotten so used to I'm a little bit stuck because I'm used to thinking of it this way, and then here's where the delaying of the exam has also come back to kind of bite you, right? Because now you want to focus on the exam, and because you've been focusing on the exam, you've kind of neglected the homework.
Yeah.
So I get it. I mean, while I was trying to be helpful to you guys too, I also see it being like as kind of a swift, like kick to the stomach, right? It's like, oh man, I'm gonna pay the piper one way or the other. But I'll help you guys. Don't worry.
Thank you.
I can sound tough and mean, but I want to help you. Part of the reason I am tough on you is because if you guys don't have this material down, it's going to come back to bite you, right? And so I have a student in my Calc 2 class who didn't know the quotient rule, and we were doing a simple problem where I happened to ask, hey, can you do this quotient rule problem? And the person had no clue what I was talking about, and it's just like, oh man, this is going to be problematic, right? So it becomes a thing where you'll be able to get through some things, but eventually it will come back and get you. And when we get back in the classroom, could you imagine if you didn't have this material down, how hard a Calc 2 or a Calc 3 would be? I don't want that for you, so I'm trying to be like, come on guys, we all have to fight, And look, I'll be frank with you guys about me. I try to be all optimistic with you guys, But this whole being at home thing has sucked. And it's so hard to be motivated. And I'm an adult. I'm like highly educated person who, like, outside of having to do this, my life doesn't have a bunch of like difficulties in it, right? Like there's not a lot of transition in my life. It's stable. And if it's hard for me who has all this stuff that's stable, I can't imagine what it's like for people like you guys who are still trying to fight and study to move forward. Like this has got to feel like things are stacked against you. And
definitely.
Yeah, and like I sympathize because, like I said, I have all this stuff where life isn't all that crazy, but I'm having a hard time. And so that's why I try to be so honest with you guys about things, because I want you to realize, like, you're not alone and I am here to help. But I need you guys to push too, you know, so we can fight together to be successful. So
thank you. We appreciate your patience.
Well, no, I mean, yeah, I get it, you know, I get it. It freaking sucks. Okay, let me show you the next problem, and then we'll make some time to answer some questions for you on issues you might have, questions you might have. So on this next one, see how it's a product? I haven't taught you how to do anything with a product for integration. So what ends up happening here is we need to expand it and make it a polynomial so that we can work with the polynomial. So in the expansion, I'm going to get 2y squared minus y minus 1. And that's my integral that I'm going to have. Did I expand that correctly?
Yes.
So now from here, I can do the antiderivative to it. So what's the antiderivative of y squared? These should all be power rule problems, right? So it's going to become y to the third over 3. It's got to be multiplied by 2. Minus, that's going to become y squared over 2. And then this one's going to become a y. And then all of that is going to be evaluated from 0 to 2. Did I do that too quickly?
Yes.
Okay, just remember, add 1 to this, so that's a 2, it becomes a 3, so then the 3 has to also go to the denominator. This has a power of 1, add 1 to it, it becomes a 2, so the 2 also has to go to the denominator. What's going to get me a derivative of 1? It has to be y.
Makes sense.
Okay? So then when we evaluate, I'm going to get, well, I'll show you the steps. 2 times 8, I'll even be nicer. 2 times 2 to the third over 3 minus 2 squared over 2 minus 2 minus 0, right? Because 0 is going to just go. So I'm going to get 16 over 3 minus 2 it is equal to, I don't know why I was going to write a 0, that's silly. 16 over 3 minus 4, right? And then that, since I want to have the same denominator so I can get my answer, I'm going to get 12 over 3, which is going to give me 4/3, or 1 1/3 units squared.
How did you get the 0 as well in the third line? Like, did you just evaluate y like either?
Correct. So remember, it's the upper bound minus the valuation of the lower bound. But all of these have y. So if I'm plugging in 0, 0, and 0, what's that going to be?
0?
Yeah. So really there should be 3 zeros, but Do you want me to write it down so you can see it?
Yeah, so you only apply the lower bound when it's like just a variable, or like
no.
Because I see it's like
No.
-2 and -0.
No. I applied the 0 here. I just went, what's 2 times 0 to the third over 3? This will be 0, correct? Minus 0 squared over 2. Still 0. Minus 0.
Oh, okay.
All of that, when I evaluate it with this, is going to be
0.
0. Now, had this been a 1, I would have gone -1 here. In fact,
Oh, okay.
does that make sense?
Evaluate each one, and then it's the same. So then just.
It would have become a +1 because it's a minus sign in front of this. So since that would have been a -1, the minus sign in front would have made it a +1.
Okay.
I'll do a couple examples that have upper and lower bounds so you can see it. Okay.
Okay.
Okay. Now this is this goes back to something that we learned from derivatives. So do you guys remember what the derivative of a to the x was?
Oh my god.
X minus 1.
What'd you say?
X minus 1.
Oh.
Yeah. Gerardo almost had it. It's a to the x ln of a. Okay, so in order to be able to get the integral of this thing, the integral of this is going to be, notice in the derivative, the ln is as a coefficient, correct?
Mm-hmm.
In the integral, it's going to be in the denominator. So it's going to be a to the x over ln of a. Now, I'm going to explain it to you guys so you guys can understand it, okay? So I'm going to go from the integral back to get what the function is, okay? Does that make sense what I'm saying? So I'm going to go from here back to this guy. So remember, from the fundamental theorem of calculus part 1, if I take the derivative of an integral, I should get the original function back. So that means I should get this back if I take the derivative of this. Okay? So watch. If I take the derivative of this, ln of a is a constant, correct? Does everyone agree with that? So I'm going to get 1 over ln of a, whatever, who cares, derivative of a to the x. But what is the derivative of a to the x? I gave it to you up here. Isn't it this?
Mm-hmm.
So I'm going to get 1 over ln of a times a to the x ln of a. Well, what's going to happen to the ln of a's?
You're going to cancel.
And I get a to the x. So, these are two things you should know. Can you guys feel the tsunami?
What?
The tsunami of mathematics coming at you?
Oh, yeah. It's too much.
It just means you need to study. Felt it since August. You can always count on Ray. All right. So, looking at the example that I have for you then, what would the integral be of 10 to the x?
10 to the x?
This
would it still be the same?
It's this.
If we're using this type of logic.
Yeah, so this is the integral, right? The a is 10.
Yeah.
So my answer should look something like this.
Gotcha.
So then from there, shouldn't it be 10 to the x over ln of 10? Does that make sense?
Yes.
And then we're evaluating
It
that.
would cancel out. Yeah. Oh, okay.
We're going to evaluate it from 0 to 1. No. So the reason I did this was I took the integral piece and then took the derivative to show that it in fact was the integral. I was doing like a mini proof.
Okay, just proving.
Yeah, just a little mini proof.
Okay.
So then from here, I'm going to evaluate, right? It's f of b, right? Capital F of b minus capital F of a, the fundamental theorem of calculus part 2. So I'm going to get 10 to the first power over ln of 10 minus 10 to the 0 power of ln of 10. So that's going to give me 10 over ln of 10 minus 1 over ln of 10, which should give me 9 over ln of 10. But if you don't know this box that I just did, this problem, you're pretty much dead in the water, right? So it's something that you will have to study and understand and memorize.
Do you ever like evaluate the natural log, or is it kind of just there as like a variable thing? Because I know how there's like...
It's never a variable. It's a number. It's never a variable. ln of 10 is a number.
Oh yeah, but it's like, you know, because we don't like evaluate like 9 divided by, like, could you do that? Or do you
Sure we could. Yeah. I'm into pretty. But if you want me to give you the approximation of this, I can do that.
Wait, I just wasn't sure because you know how there's like the n in like the other like integral stuff, and it's like you kind of just use n. It's just like kind of there, but you never really like change it. So I wasn't sure. Oh, I might have been incorrect. Don't quote me on that. But
no worries. Here, I'll tell you. It is. Oh, see, this thing's.
It's 3.9. Oh wait.
My calculator, yeah. So look, this is the same as 3.90865. The 9 over ln of 10 is just more satisfying to me. I don't know.
So if we were like given a test and you put like this question on there, would you want us, if you didn't say evaluate, like would you want us to keep it in that form, like, you know?
Okay, so careful with your language. By me giving you the integral from 0 to 1 of 10 to the x dx, I'm asking you to evaluate.
Okay.
Now, what your answer is at the end, 9 over ln of 10, 9 over ln of 10 is an exact answer. This is an approximation. So whenever you go to decimals, ln of 10 is not a rational number, right?
Yeah.
Or at least I don't think it is. I don't believe so. So whenever you're going to evaluate that, you're going to get some. Yeah. See, I only have my float at 10 at 6. So if I make my float more, you can see I get even more decimals. Ln of 10 is not a rational number, and so it's an approximation. So typically we want to be as precise and accurate as possible, so 9 over ln of 10 is way more precise than 3.90865 whatever. You know what I mean?
Yeah.
So it isn't a thing where I'm not like evaluating, I'm just trying to be as precise as I can. Right, so if you were given like, okay, area of a circle, right, and you got 4 pi, what's better, 4 pi or 4 times 3.1415928?
Yeah, 4 pi.
Yeah, it's accurate, right? It is precisely right. So that's all we're doing.
Okay.
Okay. So let me show you some funkier problems. Okay? I'm going to make them up so you guys can see these problems. So let's say that I gave you the derivative. So I'm going back to the fundamental theorem of calculus part 1. And I said, I don't need that. I went from x squared to x to the 4th of t to the 3rd dt. So remember, in the fundamental theorem of calculus part 1, I said take the derivative of the bound with the variable and then plug it in, correct?
Mm-hmm.
So then if we understand this, what should I write down?
4x cubed and then like to the 3rd power.
Okay, that's 4x cubed.
No, but then like wouldn't you put it in parentheses to the 3rd because if it's like t to the 3rd?
Oh, I see what you're saying, like this. Okay. What goes in the brackets? What goes in the parentheses there?
Would it be 3x squared from the t? Or would you do the 2x from the x squared?
So 3t.
No. So here's where it's so important you guys get it. Jose's got it. It's the actual upper bound gets plugged in. So it's the upper bound. It's the derivative of the upper bound. The exponent stays, and then that gets plugged in for t. Now the lower bound, because now we have a variable there, it should take the derivative of the lower bound, and then that plugged in to the 3rd.
Okay. Makes sense.
So I should get, what's that going to be? 12, 15. So 4x to the 15th minus 6x to the 7th. Do you follow?
Yeah.
Okay, so
It's like, this is like product rule, right? A little bit, like derivative of 1 and like the normal one.
product rule?
Or shoot, gosh, that's why I was scared to use words. No, but it's like, 4x cubed is the derivative, but then x to the 4th is just like the number, or just, it's like unchanged. Like there's like something like that, like f minus g prime, and it's like that, like kind of like this is similar to that a little bit, yeah. Is that rambling?
Yeah.
There was like one of like the rules we did. It was like chapter 2 or 3, where it was like in parentheses f minus g prime, and then it was like you did the derivative of 1.
You're talking about the chain rule?
I don't know. I kind of forgot what I was like. I know what I'm saying, but I can't get it out clear. I get what this is though, and that's all that matters.
Have a cup of coffee, buddy.
Yeah, I'm not a coffee boy.
Okay.
Never mind. This makes sense. I understand why you plug things in.
Let me give you another one and see if you guys can get it, okay? So let's say I gave you 3x and x squared, and let's say sine of t squared dt. Because in order for you to demonstrate that you get it, you got to be able to do the problem without me, right? So let's see if you can do it without me. Did you get it? So while you guys are studying tonight, I'll be doing this. I've been waiting for a long time. Over 30 years.
I hope you have a Dodger dog for me then. You can order them and they'll Uber it to your house.
Are you serious?
Yes, all of the Dodger foods, they'll deliver it to you. Dodger dogs, the nachos in the cap, all of that.
Nice.
Just so you know.
Dude, thank you. I'm gonna do that. What? Like, how do you order it?
I think you go on like here. I'll find it.
Thanks, Ray. All right. So Jose, you're right. Ooh, bummer. Didn't mean to. So the derivative of a oh dang, that's true. It's the derivative of the top, right? So the derivative of the upper bound is 2x, then sine of x squared minus my cool. Thank you. I'll take that out. It should be 3 sine of 3x squared. So then when we clean it up, I'm going to get 2x sine of x to the 4th minus 3 sine of 9x squared.
Okay.
Got it?
Yeah. I accidentally squared the signs because I like put it in like its own like function.
Yeah.
But
Careful with that. That's totally different.
Mm-hmm.
So that will mess you up, but the gist of this is what matters. Okay. So I feel like you guys get the fundamental theorem of calculus.
Mm-hmm. Yeah.
So let's look at the fundamental theorem of calculus part 1 or part 2, and let's see if I can have you guys better understand it, okay?
Sure.
So I'll just give you a problem. I'll make it up. 2, 3. How about we do something that we know? So here's the philosophy that goes into being able to solve these problems, okay? You guys ready?
Mm-hmm.
What function has a derivative that gives me secant squared x? Perfect. So tan of x evaluated from 1 to 3. So then I would get tan of 3 minus tan of 1. But see, if you didn't know that the derivative of tangent is secant squared, you're kind of stuck. So one of the strong recommendations I have for you is for you to write down all of your derivatives so you can look at them going backwards and forwards. Does that make sense? So let's do another one. Integral from 2 to 4 of I'll make it something somewhat doable. How about x cubed dx? So what is the antiderivative of x cubed? Hint, hint, power rule for integrals. Perfect. So it's going to be x to the fourth over 4 evaluated from 4 to 2. So that's going to give me 4 to the fourth over 4 minus 2 to the fourth over 4. And that one simplifies, right? This one will become 2 squared. So 4 to the fourth is 16 times 4 is 64 minus 4, so it should be 60. If I did that math right.
So I see, like, it makes sense the first one, because it becomes 4 cubed, right? Because you cancel a 4 when you have 4.
Oh yes. Yeah.
But then how do you get minus 2 squared?
Okay, so 2 squared times 2 squared is 2 to the fourth, correct? And what's 2 squared?
4. Oh, so you take it, you factor out like a 4?
Yeah.
Okay.
Yeah, I just did it in my head. But does that make sense, the fundamental theorem of calculus part 2, how it's the upper bound, the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound?
Mm-hmm.
That is the fundamental theorem of calculus part 2. The thing that's going to get most of you stuck and where you're going to have to struggle is the backwards thinking of the derivative to the antiderivative. And that's going to take practice. Okay? I will not put this homework up till Wednesday evening after you've taken the exam, or Thursday evening after you've taken the exam, because you guys need to practice and get ready for the exam. Okay? But the exam does capture 4.9. So that's something that you guys should be prepping for and looking at.
What were the sections of chapter 4 that the exam were on? I remember you said it was like a couple, but I don't really remember.
Okay, so we did, actually, let me look.
And we still get like a cheat sheet, right? Nothing has changed with that?
Oh, yeah.
Okay.
So the only thing that we didn't do, so it should be 4.1 through 4.5. Now 4.5 I didn't cover. It's just using all the information from 4.1 through 4.4 to graph. So there might be a question on that. Maybe not. 4.7 and 4.9. So for sure, these 4.9 is just a culmination of 4.1 through 4.4. There's no new material there. It's just putting that material together. In fact, you know what? I'll do this one with chapter 5. So just worry about 4.1 through 4.4 and 4.7.
4.1 to 4.4 and 4.7. Cool.
Does that make sense?
Yeah. 4.5 won't be, and then 4.9 we'll worry about it later.
Yeah.
Cool.
I can put up a practice quiz or something on WebAssign for you guys to try for the exam. But I didn't make a review for you guys per se. The exams that I had from before, let's see if I have one on chapter 4. Yeah, see, this is one that I did. See, this is one of the exams you would have gotten from me. This is chapter 5. let's see if I can find if I have an exam 3. Oh, I don't have one on here. But you can...
Professor, so we're not going to do 4.9 and 4.7, right?
4.7 will be on the exam. What won't be on the exam is 4.9 won't be. But these will be on the exam. 4.7, that is like big. 4.7 is your optimization stuff. That's where the word problems come into play. And, you know, there'll be a classic example that I'll do for you. So when you look to study that, the optimization, you know, there's typically problems like, all right, here's some parabola, maximize the rectangle inside of it. Those types of problems will be big. Let's see, what's another one? I typically do a race one for my students, but I won't do that to you. There's an example that I do in the notes too, where I talk about like a soda can and minimizing material usage. So you optimize the material usage. That's all covered in the lecture from 4.7. And then 4.9, I guess someone was saying I didn't put that in the video, so I'll put that up for you guys to look at and for you to reference, because that's the antiderivative. That's just backwards thinking of the. Derivative. Actually, let me stop recording so.